Hello everyone, and thank you for attending today's webinar on transformer protection. You can expand your slide area or maximize it to full screen by clicking on the arrows in the top right corner of the slide area box. If you have any questions during the webcast, just click the Q&A widget at the bottom of your screen. We'll answer as many questions as possible after the presentation. For the best viewing experience, we recommend using a wired internet connection and closing any programs or browser sessions running in the background that could cause issues. Webinars are bandwidth intensive, so closing any unnecessary browser tabs will help conserve your bandwidth. Some networks cause slides to advance more slowly than others, so logging off your VPN is recommended. If your slides are running behind, refreshing the page should solve the problem. You can find additional answers to some common technical issues located in the Help widget at the bottom of your screen. I'd now like to turn the presentation over to Christine Kreitz, Technical Application Engineer at Grid Solutions. Christine, the floor is yours.
Thank you, Colleen. Hi, everyone, and thank you for taking the time out of your busy schedules today to tune into today's technical webinar on Transformer Protection Basics, the 4th edition in our monthly Tech Talk series. My name is Christine Kreitz. I'm a Protection and Control Technical Application Engineer for GE Grid Solutions. I've been with GE for about 7 years as of yesterday, but who's counting? I spent my first couple years on our multi-line tech support team out of our Markham, Ontario factory, and then in late 2014, I relocated to the US to join our application team. I'm currently based out of the Cleveland, Ohio area, and I primarily support the Midwest US, although these days I'm a little all over the place. I see a lot of familiar and new names on our attendee list today, which is great. Again, thank you all for joining us. The intent of today's webinar is to focus on a few of the fundamental transformer differential protection elements, why we need them, and how we come up with some of the relay settings. We'll talk a little bit about the different types of transformers and transformer faults, then spend some time going over protection basics, how current differential protection works, and some of the challenges associated with properly employing it. Lastly, I'll briefly show how the relay settings we review look in terms of being programmed into a GE relay. All right, so let's jump in. Transformers come in varying shapes and sizes, but they all have a similar purpose, primarily to step down or step up the system voltage, or in some cases, to just provide electrical isolation or stabilization. In the PNC world, we're generally referring to transformers at operating voltage levels, usually of at least 4160 volts on the low side and above. Beyond this point, really, no matter what size or kind of transformer you have, simply put, they're just plain expensive. Transformers are one of, if not, the most critical and expensive asset in a substation. If your transformer fails, basically everything downstream of it is affected. Designed in redundancy is common in some form, but very rarely will people keep spares on hand since, again, they're expensive to buy and upkeep, and well, they don't exactly fit in a stock room. There's also usually a long lead time to repair or replace the transformer. I mean, with all things, equipment failure is inevitable at some point, but with proper protective relaying, we can try to detect an abnormal condition or fault earlier and limit the damage to it, which ultimately will have a huge impact on the repairs, the downtime, and the cost. If any of you have ever witnessed a transformer failure or seen any of the videos circulating online, you know that it typically is not a case of the transformer just stops working. It could potentially be a catastrophic failure if a fault is left uncleared or not cleared fast enough. Because most transformers are oil fields, an explosion is a very real risk, and at that point, it's a risk to the other equipment around it, and more importantly, to any people around it. So proper protection is important. There's several different types of power transformers that we need to protect. The largest transformers you'll see are generator step-up transformers on the left here. Typically, when we say a GSU, we're referring to the enormous transformers you'd find in power plants or other points of generation. The output of large transformers are usually at something like 18 kV or so, and we use the GSU to increase the voltage up to a transmission level voltage, say 69, 115, 230 kV, or whatever it may be. Because of the sheer size of these, redundancy is uncommon. Sometimes the GSU will be built into the generator assembly itself, but in any case, whether the protection is combined into the generator relay or a standalone transformer relay, it's absolutely critical to have adequate transformer protection for these. Most of us more commonly will end up working with step-down transformers. These could be substation transformers that step down the higher transmission voltage to a medium voltage that gets further fed to our distribution network, or different loads in industrial plants. Or it could be a medium to low voltage transformer within a plant. Or we could also have smaller step-down transformers further downstream in our distribution network. Something similar to the green box you see here that you might see around in neighborhoods. With these though, and anything smaller like your single phase pole mount transformers, protection is still important, but it's probably not something you'd put a full-blown transformer relay on. You'd probably rely on other overcurrent backup protection from feeder relays or even just fuses. Lastly, we could also have an auto transformer, which we show on the right here. We don't see these as often, but they do have some advantages, like they're smaller since they only have one winding. They're more efficient. You can effectively change the ratio by tapping it at various points, and overall, they're usually cheaper. However, because there is only one winding, there's no electrical isolation between the two sides. So if a fault does occur on the load side, it'll be directly reflected to the source side. And if a winding fault occurs, full input voltage could potentially be applied to the secondary system, which could be very damaging. Because there's no isolation, the secondary side will still see the transients and harmonics from the primary, and proper grounding can also become a concern. In certain cases, an auto transformer may still be more economical, and where those are used, most mid to high-end protection relays will still support them. All right, so now let's get into more detail on types of transformer faults and how we deal with them. The first category we'll talk about is external faults. That's any fault that occurs outside of and independent of the transformer. It's not necessarily a problem with the transformer itself, but external faults could definitely have an impact on the health of the transformer. So an external fault could be an overload. Excessive loading means high current. Typically, the transformer would either be overrated to account for higher than usual loading, or otherwise it's often acceptable to run transformers slightly overloaded for some period of time. This is typical during summer months when everyone's running their AC at the same time. So usually we don't want our transformer relay to trip on overload. If anything, we might only have an alarm to notify us that it's operating in overload, or we might have a time overcurrent element with an intentional time delay just to make sure it's not overloaded for too long. Most transformer relays have an ANSI 49 thermal element that you could also use to cover the heating effects of overload, although it's often not used on the average transformer. We could also have an overvoltage. This might occur due to short transient conditions or extended power frequency conditions. Overvoltages cause stress within the transformer windings, which could cause insulation breakdown. To protect against overvoltages, you could simply use the 59 overvoltage element, or you could use the 24 volts per hertz function, which as a whole looks for overexcitation conditions. The transformer core flux is directly proportional to the voltage and inversely proportional to the frequency. The measured volts per hertz ratio can then give us an indication of the excitation. The ratio should be within a specific range during normal operation. So if there's an overvoltage or under frequency condition and this ratio falls outside of the range, an overexcitation may be occurring and we can trip on that. The third type of external fault is under frequency, which, as we just spoke about, would be detected by the volts per hertz element. And lastly, we could have short circuits. Even though short circuits can cause mechanical stress within the windings, we typically do not employ short circuit protection specifically within our transformer relay for the sake of having proper selectivity of our protection scheme. The transformer is usually sized accordingly to be able to deal with a short-term short circuit, and we depend on our other overcurrent relays to clear it. The transformer relay can't necessarily tell where the fault is. It could be a bus fault, or it could just be a fault on one feeder. The specific feeder or bus relay should clear the short circuit, or worst case, the incomer relay below the transformer or the line protection relay above it will catch it, depending exactly which zone it falls in. So moving on, within the transformer itself, we can have several different types of internal faults. That'd be faults within the transformer or the transformer zone. So first, we could have overheating. That's a problem that can be caused by poor connections or inadequate cooling of the internal circulating oil, either from a blockage somewhere or loss of fans or pumps, or loss of the actual coolant from an oil leakage. Most commonly, a Buchholz relay is used, and this is an external device independent of our protection relay that essentially detects gas buildup within the oil tank, and it's usually mounted somewhere up near the bladder. Gases are produced by the breakdown of insulating oil, which can be caused by overheating, which would be a slow gas buildup, or by arcing, which would be a rapid gas buildup. In our transformer relays, we could use some of the thermal elements. However, these should be employed more as a backup or supplementary to a Buchholz relay. Since our relay is looking primarily at the electrical signals and not at the physical medium within the transformer, it might not necessarily be quite as accurate or as fast at detection. Next, we already spoke a bit about overfluxing or overexcitation, which we would use the 24 volts per hertz element for. And similar to overheating, we could also have an overpressure within the tank caused by gas buildup. A not so obvious example of this would be a small turn-to-turn winding fault that burns slowly releasing gas bubbles. Eventually, the winding fault would probably evolve, but depending on the initial severity, there could already be quite a pressure buildup. Our more advanced relays now have some pretty good turn-to-turn fault detection functions, but for general purposes, an external Buchholz relay or a sudden pressure relay would typically be used to detect pressure issues. Now, we haven't noted it on the slides here, but another major point is internal electrical faults such as winding face-to-phase or face-to-ground faults or an open winding, where we would employ our transformer current differential protection, which is what we will be talking about in detail later. Along with the Buchholz relay, our current differential element would also detect winding interturn faults, insulation failure faults, and tank faults. For most internal faults, a current differential element is used. So in the last couple slides, I mentioned a handful of relay functions. Listed here is an example of all the protection functions that our 845 transformer relay has available, noted by their ANSI device numbers. Our 845 is, I'd say, our mid-range relay, but it still has some advanced functions. Depending on the relay manufacturer and the class of the relay, you might have less or more functions listed, but you'll usually at least have the ones highlighted red here. So those are the ones we're going to focus more on today. Even though we have a lot of the functions available, it doesn't necessarily mean we have to use them all. It'll really depend on the application and the protection engineers familiar with programming them. As a general rule of thumb, for transformers rated at 2500 kVA and below at medium or low voltages, we'll simply only use our 50 and 51 instantaneous and time overcurrent elements on the three-phase CTs from the high side of the transformer. And for ground faults, we'll use an instantaneous overcurrent. On these smaller transformers, internal faults aren't necessarily as big an issue, and the transformers aren't quite as critical. So here we're just providing basic protection. Being that these are the most basic overcurrent functions, in a lot of cases you'll see either just a small transformer protection relay or even a basic feeder protection relay whose primary function is to provide overcurrent protection. Feeder relays often end up at a lower price point than transformer relays, so for low voltage applications, you'll often see feeder relays instead, but either way, the 5051 functionality is the same. For transformer 750 kVA and above, when we get into both windings at medium voltage, then we get into what I would consider fundamental transformer protection schemes. Here we're bringing three-phase CTs from both the high side and the low side of the transformer into the transformer protection relay to do, at minimum, an 87T current differential function as primary fault detection. And then our 5051 overcurrent protection, like we saw before, would be more like a secondary scheme and for ground fault protection. We also note the 63 sudden pressure relay you see here, but notice how it's shown as a separate device on the single line. Again, this would be a completely separate specialized device from the main protection relay. On larger transformers, higher voltage applications, or if you have a particularly brave protection engineer, you might use additional relay functions. For example, on a generator step-up transformer, you'll most likely also use the 24 volts per hertz element. However, for the majority of medium voltage applications we see, this is the minimum recommended protection. For the most part, unless you have a specific need to use additional relay functions, just don't. As one of our most senior guys often preaches, my favorite element is the one that's turned off. So again, here we're just recapping the most common transformer protection elements used. We have our phase and ground instantaneous and time overcurrent protection. When we say 50/80/70, we mean an instantaneous or unrestrained current differential, which we'll get into in a moment. 87T is a percent or restrained current differential, and 87 RGF is restricted ground fault protection, which in a sense is like a ground differential. This is used for special applications where you have an impedance grounded system. We won't go into this one today for time's sake, but a lot of people do use it. If you run into applications like this and need assistance, please let us know and we'd be happy to provide more information and help you out. All right, so now let's dive into some more detailed protection theory. I'm just going to briefly mention overcurrent protection. If you're interested in more detailed information, I highly recommend you refer to one of our previous tech talks posted on our website on feeder protection basics. It goes into detail on these elements. Again, regardless of whether it's a feeder or transformer relays, the principles of the 5051 elements are the same. But the basic gist is, for the instantaneous overcurrent element, ANSI 50, we're simply looking for the measured current to rise above the set pickup. If the pickup is exceeded and you have not set an intentional time delay, the relay will trip instantaneously. For time overcurrent protection, ANSI 51, there's still a pickup setting, but your time delay is based on the overcurrent curve, which would be selected as one of the curves that you see on the right here. Below the curve is the non-operate region, and above the curve is operate. As you follow the curve to the right, we're increasing the magnitude of the current, shown as multiples of your pickup. As you go up, the time to trip is increasing. So basically, the higher the fault current, the faster the time to trip. The multiple curves represent different time dial settings you can select that shift the curve up and add extra time. This type of characteristic is typical of any overcurrent relays, even the electromechanical ones. The important thing to note is that if you do use overcurrent elements, You generally do need to make sure that the time delays are coordinated with any up or downstream devices so that we maintain selectivity depending where the fault is located. Again, a lot more details on this are available in that posted feeder protection webinar. So today we want to focus most of our time on current differential protection, since that's the key element used in transformer protection and also the one we get the most questions on. So we've already touched on which faults are detected by the 87T element. That's most internal faults, which is why differential is usually the element of choice. Very generally, the main principle of operation is, as you see in the top right, we place our CTs on either side of the transformer, measuring the current going into the transformer and out of the transformer. Note that we place the CTs with their polarity showing away from the transformer. The key here is that the polarities need to be opposite of each other so that when we sum the currents, ideally your differential current should equal 0 under a no fault condition. If there is a fault somewhere within the transformer zone, the two currents will not be equal. So when we sum them, we get some non-zero value, which is our differential current. If this were a 50/87T element, which would be an unrestrained or instantaneous differential, we would simply set a pickup for how high our allowable differential current would be. And then when it exceeds that pickup, it would trip. Very rarely, I would say, is an unrestrained differential used, since it doesn't necessarily account for normal CT errors, which tend to get worse as the operating current increases. We're simply just taking the differential and operating it without any other considerations. So it's not necessarily the more secure option. What we typically use is the percent slope differential, which is what we refer to when we say 87T. What we do here is, instead of just looking at the differential current, ID, we also look at the magnitude of the current so that we can adjust our operating signal accordingly. This is the idea of using a restraint current. Our calculation is, as you see on the right here, the differential current is still the current from winding 1 summed with winding 2 or more if you have more windings. Ignore the comp note for now, we'll get into that in a minute. The restraint current is whichever winding current is the highest. And then our operating signal is the calculated differential current divided by the restraint current. So we're basically just looking at a ratio. The way we determine when we should trip is by using this dual slope characteristic on the left. So the x-axis is the restraint current and the y-axis is the differential current. If our ID to IR ratio falls below the curve, we do not operate. If it falls above the curve, we operate. And just to note, in older relays, you might only find one slope. In newer relays, you'll usually see two different slopes. What it does is it lets us be more sensitive at lower currents when the CTs would still be operating linearly, but we still take into account normal measurement errors, which increase as the current increases. And then at higher currents, we switch to the second slope, which is a lot less sensitive to be able to account for CT saturation conditions. So with this, we're able to ensure security while still maintaining sensitivity. And the purpose of the two breakpoints is to create an inverse spline section in the middle here that simply ensures we don't have a vertical undefined slope at the transition point between the two slopes. In terms of relay settings, here we have listed the 5 key set points that we need to determine to properly create this dual slope characteristic. Now, this is a slightly oversimplified explanation. We'll start with the basic concept and then add to it as we look at some of the other considerations that we need to take into account. So first, we have the pickup value. This is where the curve starts on the y-axis. We usually set this to whatever the differential current would be at rated load during normal operation, which basically should take into account the worst case CT measurement error. Ideally, the differential current would be 0, but we're not in an ideal world. So even under normal conditions, we'll still have a very low non-zero value of differential. CT inaccuracies depend on what type of CT you're using. Typically for an ANSI C-class CT, the maximum error during linear operation is plus or minus 10%. So to determine the worst case normal differential value, we basically would skew all of our winding currents by 10% and add them up to get some level of ID. Again, this is a bit of an oversimplification. It'll depend on your application, but these are the typical steps just to give you an idea. Next, the first slope is set to ensure sensitivity for internal faults at normal transformer loading. To get the first slope, we just take the rated load differential current that we calculated before, so our pickup value, and divide it by the restraint current at rated load. The restraint current here would be the vector maximum of the 2 or 3 winding currents, again adjusted for the worst case CT error like we did before. A slope value of something like 18 or 20% is pretty typical. Now to get breakpoints 1 and 2, this requires you to have some information about your CT characteristics. Breakpoint 1 should be set to correspond to the end of the worst CT's linear region. So that'd be the maximum current where the weakest CT will still operate normally, and just below the current value that would cause CT saturation due to lurking DC components or residual or remnant flux. Remnant flux essentially derates the performance of the CT. We assume the worst case scenario of 80% remnant flux in the core, which decreases the CT's capability about 5 times. This breakpoint needs to be calculated using the knee point voltage from your CT data sheets and the known resistances of your CT, your relay, and your lead lengths. We don't show all of this detail here. If you do need to do calculations, I'd recommend you refer to the relay user manuals, which have some pretty good examples you can follow along with. Now, breakpoint 2 should be set just below the external fault current level that would cause the worst CT to saturate. And when we say just below, we're looking for about half a power cycle before we see the CT start to saturate. Some people set this to the maximum linear current available value from the CT characteristics that was calculated in the last step, using the CT's knee point voltage divided by the secondary current circuit burden. This current is the start of the CT saturation region, assuming no flux. However, if you want to be extra accurate, the best way to figure out what this point should be is to use the IEEE CT saturation tool that's available online. If you just Google IEEE CT saturation tool, you should be able to find it. You can plug in the CT and the burden info and a proposed fault current, and it'll show you the measurement waveform that would result. You can modify the fault current value until you see a good half cycle of saturation-free measurement, and then use that fault current value as the breakpoint 2 setting. Again, a really good example of this, along with screenshots of the IEEE tool, are available in this case, the 845 relay manual. All that being said, every now and then I still hear from someone who's trying to set up their 8070 element, but has no information or data sheets other than the CT ratio. In this case, obviously you should proceed with caution, but you can use the relay's default setting values as a guideline. In the 845, for example, the breakpoint 1 is defaulted to 1.5 per unit, and breakpoint 2 is 4. Those are probably conservative values that give you a large transition relay region. Typically, I hear the values end up being something like 2 per unit for the first breakpoint, and without any other info, most people will set the second breakpoint to the minimum allowable value above breakpoint 1, which I think is something like 2.2 or so, just enough to say there is a transition region. We don't let you set them to the same values since that essentially would defeat the purpose of making sure we don't have an undefined slope at the breakpoint. And just a side note, some older relays, like our older 745 relay, only have one breakpoint. The last setting we have here to complete the characteristic is slope 2. This region should be set high enough to override a worst case differential current, which would be when one CT saturates due to an external fault while the other CTs do not saturate. Typically, the slope is somewhere between 80 to 98%. Our default value and what I see most often is a slope setting of 95%. Okay, so those were the key settings associated with the current differential element. Now we're going to start adding some detail to the calculations we've went over in the last few slides. Like I mentioned earlier, the philosophy of current differential is not quite as simple as just comparing the current going in and coming out. There are some considerations that we need to account for due to the inherent characteristics of our equipment. For example, CTs are not perfect. They don't provide perfect measurement. There's always some inherent measurement error, and at some point, every CT will have a limit where it will start to saturate and provide inaccurate metering. These are some things that we've already taken into account in the error margins we added to our previous calculations and the purpose of using the two slopes. Also, with the transformer themselves, there's some challenges. The purpose of a transformer is to change the voltage level. At no point is power created or lost though, which means as the voltage changes, the current also changes. This means the current on either side is not necessarily directly comparable. There's a magnitude mismatch that we need to account for. Also, most often, there's an unequal phase relationship between the primary and secondary currents, which further means we can't just directly add the currents. We basically need to line the values up first. And then lastly, we'll also talk about transformer inrush, which can cause issues as well. So as I mentioned before, power is the product of the current and the voltage. So we see here the power is still equal on either side of the transformer, but the magnitude of the current has changed since we modified the voltage. We need a way to relate the current on either side to each other to make sure that any difference we see is because the current is going somewhere else internally that it shouldn't be, and not because of the normal magnitude change. In other words, what we do is we bring the winding currents to a common base, kind of like the per-unit system. In some relays, you need to select which winding you want to use as your base reference winding. For example, that's how it works in our T60 relay. In other relays, like the 845 relay, you don't need to set anything. We automatically use winding 1 as the reference. Unless you're doing manual calculations for test verification purposes, you generally don't need to do anything here except selecting the reference winding if applicable. The relay does the magnitude compensation calculations internally. Again, the applicable relay user manual will have the formulas with examples laid out, so you can go through it in detail if need be. Another challenge, as mentioned, is the change in phase relationship from the primary to secondary side of the transformer. In this example here, we have a Y-connected primary and a delta secondary. In the phasor diagrams to the right, you can see the Y winding currents to the left. Then when we look at the delta secondary, we see that the currents lag by 30 degrees. What this phase shift ends up being completely depends on your transformer and how the windings are configured. Unless you have a YY transformer, there definitely will be a phase shift. The transformer datasheet or the nameplate should indicate this. It usually notes the standard vector group code, which indicates the winding configuration and phase shift, or it shows the vector diagram with this info. For example, it might say something like CYN1, which would indicate a delta connected primary, a Y grounded secondary with 1 indicating a 30-degree lag phase shift. Now, the way we do phase compensation can either be the older way, externally, where you essentially finagle the way the wiring goes into the relay to essentially trick it to see the same phase relationship, which is not necessarily recommended since it could potentially lead to issues with metering. Or the recommended way would be to let the relay do it automatically for you. The only thing that you would need to do is make sure that your winding configurations are properly identified in the settings and that you've set whether you've done compensation externally or if the relay should do it automatically. In our user manuals, we do list a table of what phase compensation formulas we use according to what the phase shift is, in case you do need to do any calculations by hand. So just to give you an idea of what the actual calculations look like, there's a lot on this slide here. These are some example formulas from the 845 relay user manual. You see the first thing we do is calculate the magnitude compensation factors. Simple enough. Then for the type of example transformer we have, I picked out the corresponding phase compensation formulas. And then the final compensated current values that make use of the magnitude factor and phase compensated values is shown on the bottom left. These compensated currents are in reality what we actually use when we calculate the differential and the restraint currents that we looked at earlier. So you see this to the right, shown per phase. For the differential currents, we would still add our CT measurement error margin and then still add the winding currents, but the currents that we'd use are the phase and magnitude compensated values. Same idea for the restraint current. It's still whichever is the maximum current, just incorporating the compensated values. Again, the exact way that the compensation is done is a little bit different between relays and relay manufacturers, but no matter which relay you're working with, we all list these formulas along with some examples in the appropriate user manual. And if you're ever not sure, let us know. We'd be happy to help you out. The last major challenge that we see when using current differential protection is in how we deal with transformer inrush. So when a transformer energizes, there is a huge inrush of current that flows in order to magnetize the core. During this time, there's little to no current flowing out of the transformer. Inrush current can be as high as 10 times the rated full load amp. And to top that, it's usually either not seen or not equal on all the windings. So without any consideration to the relay, this would appear as a severe differential situation and it would probably trip pretty quickly. The exact inrush characteristic is dependent on each transformer, but in all situations, the inrush current is predominantly comprised of the second harmonic. We can kind of see this on the oscillography on the right. So the first three waveforms are the phase currents, which you can see are irregular and seem to have some decaying components. The red group is the phase A differential and restraint current, and then the magnitude of second harmonic, which you can see is pretty high in comparison. Then the blue and pink groups are phase B and C, and you see that the currents, especially the second harmonic, are not the same in all three phases. The way that the relays deal with this is to look for the presence of second harmonic in the winding currents. If we see an inrush of current and it contains a certain level of second harmonic per what we set, then we can safely declare that the transformer is in energization state and we would block the differential element from operation until the transformer is energized. This is a specific setting that you need to enable, and you also need to select how many phases you want to see the second harmonic on before you block on inrush. This is a very common question that we get. So the inrush inhibit mode options are 1 out of 3, 2 out of 3, average, or per phase. If you select 1 out of 3, we look for second harmonic current on just one phase. If it exceeds the threshold, we block the differential on all 3 phases. 2 out of 3 is similar, but we look for 2 phases to have second harmonic. If set to average, the relay calculates the average of the second harmonic between all 3 phases. And if you select per phase, we look at and block each phase individually. Which setting you select depends on your transformer and how much security you want. So for newer transformers, 1 out of 3 is okay. It's less secure, but newer transformers are more likely to operate predictably. For older transformers, we usually suggest 2 out of 3 are average, which end up operating pretty similarly, average being slightly more secure. We usually advise against using the per phase since it has a higher likelihood of causing a misoperation, being that we're looking at and blocking essentially in a single phase fashion. So moving on, this last note is not so much a challenge, but more a word of caution. Every now and then we have someone ask us why their differential element keeps tripping every time they go online, even though there's no fault. Often it ends up being a matter of how the CTs are wired to the relay. So here we're showing the typical wiring diagram from the manual for the 845 relay. Notice how the CT polarity markings are pointing away from the transformer. You don't necessarily need to follow this wiring exactly, but it's crucial that the polarity of the CTs be opposite of each other so that when you bring them to the relay, their phase is 180 degrees apart from each other so that they effectively cancel each other out when they're equal. This is how we're able to summate them to get 0 differential current during normal operation. If you have the polarities going the same way, the relay will effectively add them and we'll end up with a really high differential current, which is not correct. Okay, so correct phase CT polarity is essential. All right, so we spoke about a good handful of settings. Now I briefly just wanted to show you how that ends up looking when you go to program the relay. This is a screenshot from our setup software window for the 845 relay. This is under the general transformer setup window. Here's where you input all of your transformer information. The 2 things I wanted to point out, the first setting highlighted red, this is where you select if you want the phase compensation to be done by the relay automatically, or if you've modified the wiring externally to account for the phase shift. If set to internal, the relay will look at what you've entered for the connection types under the winding 1 and winding 2 settings, as well as the angle setting that you've input in that second field highlighted red at the bottom, and it'll take care of the phase shift for you. Most of the settings that we spoke about are under the transformer % differential settings. You see here we have the pickup value, slope 1, breakpoints 1 and 2, and slope 2 values that we calculated. Once you enter these settings, if you're using a T60 relay, there's actually an option to view the characteristic that you've built. This is what you see to the right. In the middle here, you also see the inrush inhibit settings that we spoke about. You would enable second harmonic blocking, set the inhibit level, 20% is pretty typical, and then the mode where we select how many phases we have to see the second harmonic inrush on. We didn't speak too much about it, but we did mention instantaneous differential, the 50/87T. That'd be this int diff section near the bottom. If you choose to use it, you'd set it to probably a fairly high value, more as a backup function. So the last thing I wanted to mention, of course, is a quick overview of all the different transformer differential relays that GE offers. We have 4 different product lines and relays to choose from for transformer protection, depending on your application requirements. First, the 345 is our smallest, most economical relay. It's meant for smaller, less critical 2-winding transformers. We consider it to be our most basic relay, but it still has the current differential element and most of the key functions you'd be looking for, as well as some logic flexibility. The second relay here is the 845 relay, which we've mentioned a few times already. The 845 is part of our newer 8 series line, which is the next generation of the legacy SR line of relays, like the 745 that you might be familiar with. The 845 is a well-rounded relay that can be used on small, medium, or large transformers with either 2 or 3 windings, usually medium voltage. It has all the latest features and processing power, a nice large graphical display, no electrolytic capacitors, which is a huge deal, a lot of configurable ordering options as far as what protection functions you want to include with it. You can go basic or advanced. It has a lot of logic and networking flexibility, and it can also interface with some GE dissolved gas ionizers that would be mounted on your transformer tank, which is pretty cool. The last 2 relays are part of our UR product line, which are our higher voltage utility grade relays. The first is the T35 relay, which has more basic transformer protection elements. And then we have the T60, which would be the more advanced high-end critical transformer relay. Both of these can protect up to 6 windings. The UR relays have been in the field for almost 20 years now. We recently made a lot of great updates to them, like the large graphical display, more communication and advanced automation features, just to name a few, but still keeping its modular structure that most people select it for. So that's just a brief overview. Again, if you have any questions at all, please reach out to us and we'd be happy to provide more info. So just to recap, today's webinar hopefully provided you with a good high-level overview of the basics of transformer protection. Transformers are expensive, critical assets, and proper electrical protection is important. At minimum, we usually use the percent differential and timed instantaneous overcurrent functions. We went over how to come up with some of the key settings, as well as some of the major challenges that we have to take into consideration. And then lastly, a common cause of troubleshooting is due to incorrect CT polarity. So make sure you have your CT wiring correct. All right, so I think we're about at Q&A time. Colleen, would you please remind our listeners how they can submit a question?
Sure. So just a reminder, if you do want to submit a question, please click on the Q&A widget at the bottom of your screen. Type your question in the text field and click Submit. Christine, let's turn it back over to you, and you can begin answering the questions that have already come in.
All right, so let's see here. All right, so here's an interesting question to start with, more on the basic side. Someone asked, why do transformers hum? The short answer to this is that the current flowing through a transformer, because it's alternating, produces a similar alternating magnetic effect on the iron core. That causes a cyclic expansion and contraction of the core laminations, which is what produces that audible hum. I believe that's called magnetostriction. Usually the frequency of the hum is twice that of the system. So here in North America, when you walk by a transformer, you usually hear a 120 hertz hum. All right, so someone asked, what is the suggested GE transformer protection relay for 67 MVA, 2 winding, 3 phase, 230 kV to 13.8 kV? You could either use the 845 or the T60. It depends exactly which functions you're looking for, but being that it's on a higher voltage transformer, we'd probably recommend the T60. But if you have a specification or anything, more information on that, let us know. We can give you an order code and more information. Someone said, did you say the SR relays are being obsoleted? Yes, that is correct. So the older 469, 489, 750 and 745 relays have been marked for obsolescence. Currently, our cutoff date to still purchase them, I believe, is the end of 2021. We recently extended it. All those relays have been replaced with a similar 8 series relay. So we have the 869, the 889, the 850, and the 845. They're the same cutout. Settings can be converted, basically the same functions. If you're affected by this, let us know and we can provide more info to you on how to ease the upgrade process or even come in and show you the new relays to you. All right. So how can I confirm my test results to know if my differential is operating properly? If you're testing the differential element with a test set, there's a couple ways to approach this. You can do all the calculations manually. You know what the winding currents you're injecting are. You have your CT ratios. You can refer to the user manual to get the magnitude and phase compensation formulas, calculate the values for each phase, find your differential and restraint currents, divide them and see whether that value falls above or below your dual slope characteristic, which you might need to plot to figure out. Or depending which test set you're using, I think some of them do have a feature where you can input your relay settings to it. It'll plot the slope characteristics, and when you do the test, it'll tell you if the relay passed or failed. Or depending which relay you're using, we do have a differential element simulator that you can download from our website. It's basically a spreadsheet that has the algorithm built into it, where you can enter your winding and CT info, your settings, and the test currents that you're using. Then it'll plot the dual slope characteristic for you. And with your test currents, it'll show where you lie on the characteristic, whether it's going to cause a trip or no trip. If you'd like more info on where to get that tool or on the calculations, let us know. Is the IEEE tool for CT saturation free, or do you have to buy it? It's free. If you just Google IEEE CT saturation tool, it should come up pretty easily. Again, that one's just like a spreadsheet file as well, so you can save it, open it on your computer, and test it out. What if one of my windings is grounded and not the other? How does that affect the differential? Well, if one winding is grounded and not the other, and a ground fault occurs, then the winding on the grounded side of the transformer will see zero sequence current and the other side will not. And this would register as a false differential current if it's not accounted for. So in the general transformer settings in the relay, that first screenshot I showed earlier, for each winding, there's a grounding setting where you can select whether the grounding is within zone or not within zone. If you have a winding that's grounded in any way, then you should select within zone. In that case, the relay will perform zero sequence removal to the winding currents of the grounded winding. The formula that's used depends on the winding configuration, but these are all listed alongside the phase compensation equations in the user manual. Did you say that the relay can do DGA? DGA being dissolved gas analysis. The relay itself, the 845 particularly, does not do DGA itself. but GE does have some dissolved gas analysis devices. So these basically are online monitoring devices that are mounted, tapped off of your transformer tank, and it monitors components within the oil. So it looks for different gases. It might look for moisture. Typically, you have to have somebody go out to it and pull the information from it unless you have it networked. What we added in the 845 relay is that you can, via the network, pull that dissolved gas analysis information from that separate DGA device and have a report print from it in the 845 relay. So instead of having to go pull two devices, you can just look at the 845 and get all that information there. All right, so okay, so a question related to the grounding again. If both my windings are Y grounded, do I still have to set the grounding to within zone? Yes, you do. Sometimes it's assumed that because there is a ground on both sides, this provides a path for the zero sequence current to flow both in and out of the zone, so it won't affect the differential. But the seal of the transformer tank could potentially act as a quote unquote phantom tertiary that could create an internal source of zero sequence current. So if you have a single line to ground fault, you could get more zero sequence current out than coming in, which would cause the differential to misoperate. So you still need to set the grounding to within zone for both windings so that the zero sequence current is filtered out. All right, a couple more questions. What's the maximum magnitude mismatch factor I can have between the high side and low side and still have the relay do magnitude compensation? For the UR, the maximum is 32. For the 845, it's 20. All right, does the T60 with firmware 7.8 support full transformer differential protection using 61859-2LE process bus and MU320 merging unit? Yes, yes it does. I actually have a couple customers who have this installed on new projects or in the testing phase. So if you'd like more info on that, let me know. Okay, and then one more question here. What if the transformer only has inrush on 2 phases instead of 3? Yeah, a question we get every now and then and related to this is what happens if you select 2 out of 3 for your inrush inhibit mode, but no inrush shows up on 1 phase? So, you know, your second harmonic isn't going to pick up on that phase. If you're using the T60 relay and it only sees inrush on 2 phases, it'll automatically switch from 2 out of 3 to 1 out of 2 to make sure we still correctly block the differential in case that the second harmonic drops low on one of the remaining phases. All right, I think we're just about at the top of the hour now. I still see we have some questions in our list. I'll make sure for those that I haven't answered that we do follow up with you in the next little while. With that, we'll go ahead and conclude the webinar. Thank you all for attending today. I hope you all learned something new. Make sure to keep an eye out for our next Tech Talk invite, which should be early this fall. Thanks again and have a great day.